Yeah. I actually, there's lots of problems with this title, but yeah. The reason put this title is just that a question that allow you to think whether or not I answer that. You will find that really the question is not well defined, so I can give you whatever the answer because really what the prediction we didn't define here yet. Prediction in terms of short-term, near, long-term, or about the feasibility of a treatment or so on. So really, there will be two parts of this. The prediction first part we'll be referring to whether or not it can fit data, can show whether or not the next treatment cycle is feasible or not. And then later on, we'll be really trying to predict sort of month by month the treatment outcome. So we have another paper accepted about months ago. I was hoping to see Tracy, but I know she has to leave. But then this also relieved me from have to talk about her work. So this is, I want to show you this slide I just got this morning at 6 o'clock. So you can see this, this is 2008 data, what sort of like statistics on cancer incidence rate. So the number you look at is, okay, I'm sorry, I have to thank the organizer and then all those of you who helped Yang Jin. I really, I think all of us enjoyed the hospitality, and this is a great workshop to meet new people, meet old friends. And yeah, sorry that I should have said earlier. But anyway, this is a very interesting, very dynamic statistic too. Every 4 years, there will be some changes. But if you look at the number, Korea is somewhere, I think used to up. It's good. Good news. Yeah, good. Yeah. So, yeah, very good because you are. Yeah, you have to. You have to be careful. Yeah. Yeah, this is about the incidence rate of 100,000 male. What? Not percentage. Per 100,000 per year, the reported cases. Yeah. Of 100,000 male of.
Sickness or death?
Oh, this is just incidence, not the death. Death rate much lower. Yeah. Right. Of prostate cancer. Yeah. Right. It's misleading. It is very misleading. Like the China Indian, they never report, for instance. Exactly. Yeah. Yeah. So that's why I told you that every 4 years you're going to see the change. United States is 80 something, 83. Right. Ireland because they eat too much the red meat. Yeah. Yeah, well, that's one of the, and also the way how they eat can be also an issue. But that's not, I mean, this is just statistics, and the statistics cannot be really trusted. Poland is here. Very nice, very good. Okay. Yeah, but it's, if you look at the data 20 years ago, both Japan and Korea was much lower, about 1/2 of the size. So I just want to highlight the average. Yeah, exactly. Right. If you are below 70, you're better than average. The country data. Yeah. That's not my talk. I just want to flash the slide. So I just want to show that why we were sort of like attracted to this topic, not because of it's a cancer. It's rather because it's presenting challenging to model because we see the past effort and also continued challenge that facing us. If you look at these data, this is a treatment cycle over the course of 3 years or 4 years, usually less than that. This is a lucky guy that went to 3 cycles, looks like can continue for another cycle. I will talk about what's the treatment, but here I just want to show you, look at the nature of the data. The vertical axis is a PSA. Again, I have to define. Yeah, PSA level. And then this is a day. This is one patient. We have 7 patients data. That was 20 years ago. And the data 20 years ago actually is better than nowadays because the data we get, even I talked to people from Johns Hopkins. I mean, they actually tell us that work with the data we have because that's a good set of data. Yeah, this is, yeah, right. For now, just look at the data. And I will explain this later on because really I just want to give you what's the difficult, what's the challenge that's facing us and why we have to do what we do later on because the model also requires some time to explain. So this is, each one is a treatment. So basically you take the drug that they're going to block the androgen production, and then you can see the PS level goes down, and then you have some holidays for about usually 6-7 months, and then let the PSA level go up, and then usually from 10 to 15, 20 certainly is absolutely up threshold that the physician will start the new treatment. So the more conservative will be 10, between 10 and 15. So start treatment goes down, and once goes there, and it goes up again, as you can see. So usually we are not seeing anything peaks about 20 because that's viewed as a dangerous zone. And so this is something that the blue line is simulation. The red dot, the data, and then these dashed line is we use the spline basically to feed. Yeah. Right, and it's not by luck. We have 7 data, 7 patients that more or less they all. But the other patients data we have, they don't have so many cycles, so you are not going to see the. Not because of this one. This we only take the last cycle to predict whether or not we can have another treatment. So in this case, the treatment will be whether or not you can go for another treatment. If the PSA level stays above 10, then usually this is cautious level. If it's above 20, then you should either take the patients off from the androgen ablation treatment or should let it stay on as continuous treatment protocol. In this case, the prediction we had, we only want to tell whether or not this patient can can continue for another cycle. Yeah, and these are the right, and then now, yeah, this is for the prediction phase. So again, I mean, this is supposed to show up at the last, but I don't know how long. Yeah, it will take me to get there. So I want to show the punchline first. Right. No, the very first is not punchline. Actually, this is it. Yeah, this one shows that you can, because we talk about the title, talk about the prediction. So the prediction in a very, very sort of like general sense. In our case, for physician, they really want to know whether or not they can go for another cycle. So if that's what's the prediction is about, then more or less, yeah, we can do the prediction. Yeah. Right.
Your model predicts that you will have a big rebound.
No, this means well, if the patients, well, this is not means great. It means that well, if you for the intermittent treatment, so that's will be the time to let go of the because this is the drug is on, so PSA is going down and stay down. The question is whether or not the patients can be given a holiday of a few months of vacation. So of course it will go up, shoot up. And so the question is now if with the treatment placed on, whether or not we come down. So in this case, it shows yes, this particular patient will be okay. And then there are cases where the disease is in the later stage, then you cannot. And then you can, okay. No, no.
Deprivation. So it was a continuous treatment. Is that
Yeah, this was off treatment, and the treatment start and goes down, and then the question is if now we let go of the treatment, so what will happen? The PSA is predicted to rise, and then if you start the treatment, so the model shows will come down.
What is the disadvantage of stopping the treatment? Is the treatment expensive? Does the treatment have
The resistance,
side effects?
toxicity, the quality of life.
Or drug resistance?
And for many patients, actually, it's quality of life. The loss of a lot of the sex drive and also lots of other physical. Well, I will show you that. This is always the danger for.
But it's better than die.
Well, that's true for most of us, but some patients. Right. I know. That's what they say. I think it was a mistake. Right. I think I made a mistake. I should have left these at the end. So I'm going to fly through this. I think most of us already know the position and the function of the prostate. It's really a Chinese chestnut shape, but they call walnut shape, which is fine. And then it's below the bradus and in front of the rectum. So you do the physical check. The physician can touch, can really tell the shape, the size. But really what sort of make the prostate cancer screening so powerful, so influential is, of course, the PSA screening. So you look at the treatment option, and of course, it varies from patient to patient, from also physician to physician, also from depending on your PSA level. But for advanced stage, you are advised to take this hormone treatment, which really akin to castration, and then you really block 95% of the androgen level because there's still parts of your body will produce a small amount. So the biology that really sort of behind lots of the models in the literature really can be described by this cartoon, and this was from this now became the most influential review paper on prostate cancer. It's already due. I think it's due for the second version. We have, if you look at the androgen, which really required for the prostate to grow and also to regulate its death. The process typically takes the form of the testosterone, so it goes inside, and then they really oftentimes, 95% of the time, we turn into they had this DHT form, which are really much easier to be to bind the receptor, and then so this complex goes into the nucleus, and then more or less that's where the regulation of the growth and also death, and including also production of PSA is much increased. So that's really the biochemic change. If you want to go to the molecular level, then you have to really have these equations for AR complex and so on. And but then we don't have the luxury. In our case, the data doesn't provide any hint of these ones. So we won't need that much of detail. So we will focus on how much the androgen, the testosterone, sort of will be needed in order for the cell to proliferate or to die. So at least you can see the dependence of the cell growth death on the androgen through this diagram. And so further discussion about the need or the effect. So this is in response to Ursula's question. I mean, this is just very few of the adverse effects on the patients if you have a prolonged treatment. And if you So so this is actually 20 years ago, 25 years ago. There's already people talk about the intermittent treatment. And now we already heard a lot of this quasi-intermittent treatment of other diseases, other cancer. But I think for prostate cancer, this was very much sort of like viewed as a good alternative because it was really promoted as a very, very desirable alternative. And the models depends on what the model formulation, which school, how much detail you put into that. We give sometimes contradicting or maybe revealing details. So the intermittent therapy will be more or less I already described through the case diagram. You stop treatment if you see that the PSA level stays low. And PSA level, of course, is indicative of the growth activity of prostate cancer. The faster growth, then there will be more production of PSA, and then the level will increase. And so that's really, it's highly correlated. And of course, PSA level also can be highly correlated to the volume. So that's also always an issue. And then, of course, if you really into the accuracy of that, I probably have a slide to talk about that. There's always 20% false positive, 20% negative, false negative result on PSA screening. So I will have a better slide to talk about this one. Actually, I don't have time to go over much of detail. It's much easier for me to just show you this. This is an actual case of patients. Androgen level and also PSA level over the course of a very long time. This is a patient, a lucky one. Patients that you have about 8-9 months treatment. So bring down the PSA level to really low. This was 20 years ago. At that time, the equipment can only detect the 2 nanogram per milliliter. So they really let it go on below the detectable level for a few more months. And then they think enough is enough and they let it go. And then they were sort of like cautious. They choose, in this case, this is a group of urologists in University of Alberta at that time. And then they moved to University of British Columbia. And then now they set up the workshop as a Canadian urology center and has a lot of cases. So 15 was the point that they will switch on the treatment, and so roughly you have half of time you have treatment, and half time you have vacation from treatment. So the patients has sort of can resume to normal life, and the most importantly, they argue that it also postponed the inevitable resistance, and this actually talked about by a paper I will. Mention that later on by Avner and Hashjan in the PNS paper 3 years ago, and they really look at if your model doesn't really differentiate the evolutionary feature of the interaction, then you will get a wrong result. So the debate still rages on a couple years ago, and then this was actually. The result is published in 2011, but then 2 years ago, if you remember, in the United States, we reversed, the government reversed the recommendation. 3 years ago, every man of like 40 years old should go through screening, yearly screening, and then it's 180-degree turnaround saying that no one should go through screening because for each patient saved, there's about 1,470 unnecessary treatment, and many of them resulting in actually very, very harmful outcomes. And here, this is sort of like talk about. I'm not talking about screening, and really talk about the treatment, the intermittent treatment versus continuous treatment. The earlier reports, most of the early reports, will argue favorably for the intermittent treatment. But I think due to this sort of like early report of the success, so many patients, I think, prefer to have quality of life rather than a few months of additional suffering. So I think the statistics shows that there's a slight more death rate among the intermittent arm of about equal size, about 750 each. So really, so the conclusion is that this is very, very comprehensive study. I think it shows that indeed intermittent androgen suppression is indeed comparable. It's a good alternative to the continuous treatment. So that's sort of like, in a way, confirms what people already know. But put lots of argument to a little bit rest. Schools like Johns Hopkins, for instance, they still very much vehemently defend for the continuous treatment. I think the drug company also will like to argue for the continuous treatment. So the data we get is really old, but we really prefer to work with the older data. We have newer data, but the quality of data, you can see that well, the reason this the set of data we get was so nice is because they have to really prove the concept. And then this is done by this resident, the Japanese fellow, who is really, really serious about what he's saying and what he does. And he basically spent 3-4 years. And I had a lot of respect for the data that collected by the Japanese researcher over the last 20 years. When I whenever come with data and I can see the care they put, I mean, I have the spreadsheet. I mean, he really, really collect a lot of information. So they started on the mice data and showed sort of promise. And then, so they recruit 7 patients, and then they did the same in this intermittent treatment, and it works just as they expected. And then they moved on to have a couple of hundred patients, but we are going to just use the first proof of concept set of data. So I think for this audience, we don't need to really talk about the necessity of mathematical models. But for physicians, they really like to see how we can personalize of the threshold values, including like how low should be low enough to stop and how high you should start switch on. So these ones are variable. The guideline now is 10 to 20. Europeans will say 10 to 15. And then some more conservative physician here, they go above that. Yeah.
So when you say that the on-off, length of the interval on and off, decided based on doctor experience?
No, by the PSA level.
Yeah,
but also by the, yeah. Right.
Yeah, so doctors basically a little bit at the moment experiment on patients.
Right.
They give some longer and see how it is and how
Exactly. Right.
So it's, yeah.
Subjective, yeah. So
Clearly there is a need to do it
that's exactly right.
without exposing people
Right.
to mistakes.
Right, exactly. And then they don't have to, I mean, if once this became sort of published, and then technically they don't, they can sort of better defend themselves in the court. So yeah, so I don't have to go through this in detail because Tracy's not here, but then really much of the recent models are more or less based on her work 10 years ago. She really did a very, very careful, excellent job in terms of explain what should be included and why these variables should be studied. And very, very nice paper. Not this one. This one is for analysis, but she's first published in 2000. I mean, I think this was, I want to remember, we had debate. And Hans had this malignant mass picture in his last slide. It's really the economics journal basically interviewed some of the contributors of that issue, and then so put out that article. The big, right. So and myself also have a paper in that issue. Anyway, I want to sort of like do some justice for people like Swan Sam and who did really nice work, very simple work. 3 years prior to Tracy's, I mean, of course they all were students for Jim Murray at that time. So she actually, based on data, and did a very nice, simple correlation of volume and the PSA data. And that work sort of allow us to feel comfortable when we make assumptions about how the PSA should be modeled, I mean the production. And then the biological implication was beautifully documented in Tracy's work, also 2004, but that's actually a year after this paper, or model paper was accepted. And then what really brought us in is this paper by also this Japanese group, by engineers. These are a bunch of engineers and pretend to be mathematicians. They actually did lots of mathematical analysis, but the purpose was trying to see whether or not the model can actually fit the data, because the data is highly nonlinear. You want to have a non-autonomous or autonomous equation that with minimum number of parameters, and to show not just fit the cycles, but also the amplitude, the peak and the trough. And that's tremendous challenge. Unless you started, worked on this one, not because these are individual patients. They really various in terms of amplitude and also cycle, also the period. So they did very hard work on that. I think it's very good work, but it took them 2.5 years just to publish the work. So the author, ended up frustrated and left the academia area. Actually, stayed home. It's but really beautiful work. And so 3 years, actually more than 3 years now. It's really about 5 years ago. A group of us was contacted to contribute article to really, it's actually start the mathematical biology section of Biologic Direct. This is a open access journal that many universities are supporting that. So if you are one of the lucky university faculty member, you don't have to pay a dime to publish papers there. So so this is for like Darwin's 150 years, I think, anniversary issue. So we had a lot of time. We spent a whole year to work on this paper, and then we cited 99 papers, and then we really feel ready to work on data. So this is prior, we have the data. And so undergraduate student come along, took my class, and then we start working on that. But I would like to really, because talk about the PDE models. The Tracy Jackson's model is a PDE model, but then she really used the radius image, so quickly turned that into, in essence, an ODE model, even though her analysis is really she really find a lot of biological reasons to simplify the model to perform the analysis. But this is a free boundary problem that very nicely done. So if you want work on PDE models of prostate cancer, you don't need to worry about existence and uniqueness. It's all taken care of by Avana and Hash, and they even probably can share with you with the code because they run very beautiful simulations there. So I just want to make this comment. I am short of time, so I'm going to go quickly talk about the model formulation. The model formulation by IDAT, the Japanese group, is really, if you remove the spatial component of Tracy's equation, and then you find that they are more or less just taken out from Tracy's paper. The two phenotype, X1T, is called androgen-dependent population, and that's fine. In fact, all cells, cancer or normal cells of prostate, they actually need androgen. But in this case, we actually still going to call androgen independent, even though it's actually dependent. And Tracy made it very clear that because you still have that, even with unless you have a total body blockage. But there's a lot of pathways to really render the androgen blockage probably powerless. What we have here also, this is androgen concentration because we are going to use this as a variable that's going to model the growth rate, the switching rate, even the death rate later on. So we do need this variable, and in the data case, this is what's given. So in a way, we have this variable, but actually also we have data, and also we have data on this, so we are going to use this and hopefully use that information and our model to predict the PT. And that's really the original idea of the Japanese group. And the equation, more or less, if you look at the terms, they are just really taken from Tracy Jackson's. And these functions are also taken from her paper, except this one, because Tracy's paper, she conceptually assumed that these two populations are really parallel. They never switch. Because for probably good reason, because she was looking at the mice state. That's only for a couple months. So there's really, in that short period of time, there's probably not enough time to do the switching. But now you look at the patient's case, and then there's a long time for switching for the population, for the androgen dependence to switch to androgen independent one, because the phenotype. Also, you can argue that you can interpret the two populations as like one fast grow, one slow grow. So it can allow alternative interpretation. And so this is a sort of a Christian Swanson's sort of contribution. The prostate, the PSA level is really proportional, correlate to the total volume. But then of course the two populations each will contribute with different rate. And this is how we're going to interpret the data, because we have androgen data only monthly. To fit into the equation, we need to have a continuous data. So this is the Japanese group's invention, but that's also come from the playbook of Tracy. She also used this in her simulation. And then, so if I really have to go fast, most of the parameter values come from the Japanese group. That's the 14. And then this also come from another paper that by physicians, urologists in the early 2000s. And so you can see the fitting. They tried very hard. They iterate the model also a few times before they published. They tried very hard. They're very excited that at least they can fit one cycle. But it's hopeless to do much better than that. And that's actually, arguably, it's because they use, this is really intrinsic weakness of all the models we see that in theoretical setting, because we assume all those models are constant, have lots of coefficient as constant. So inevitably, we'll see something like that. But then in reality, those variables are highly dynamic. So I will show you that why we are excited by our new approach. And so initially we are excited that we by the Japanese group. Yeah, I did the model. Yeah, exactly. No, not very good. So they were more or less disappointed. So they didn't even bother to publish in anything sort of like a live science journal. So they turned around. They find the model is tractable computationally, so they did bifurcation analysis, so published in nonlinear science. And so we think, because we did a lot of data fitting and also highly nonlinear dynamics and also very complex dynamics that we observed in ecology setting. That's why, I mean, it's fitting for this workshop. We basically, we learned, we did in the last 15 years, lots of experimental work, lots of modeling, not just qualitative but also quantitative fitting to data. In fact, we used this Jupe equation modeled very nicely on the arch lipid production. So the Jupe equation is something that it's not in any sort of like a mathematical biology textbook, but it should be. The Jupe growth rate equation. Equation is really mu equal to mu m 1 minus q over q. So if I don't have time to talk about the rest of the model, but if I can explain this, then will be really nice. This is a mu m. The growth rate, if you look at cell quota, typically take this curve. And you can really, if you have a very, very experienced lab assistant, you can really do a lot of growth of cells, and you will find that they all almost invariably fit this curve very beautifully. The data points almost sort of like always fit in the curve. And then you have a little q, you have a mu m. The q is really when the cell not growing, and then you take out the cell, and then you look at the cell's nutrient quotation. I mean, how much nutrient, the limited nutrient. And then, of course, and then you give a maximum amount of nutrient and see what's the maximum growth rate, which is mu m, because then other things will be limiting. But if you control your setting, you will find that, so this is a growth rate equation that probably akin to Newton's law of motion. If you know the acceleration, then you can talk about speed, and then you can also talk about the position. I think for cells, there's lots of other things that we cannot tell, but for growth, usually you can identify what's most limiting. And so this is very nice. And also, it shows, it allows death rate, if the death is due to nutrient going below the little q. So the death rate can go to infinity if the q goes to 0. And so if you look at all the population models, cell models we have, that naively allow, say, if you stop the nutrient supply, the cell can still exist for a long, long time, and that will allow finite time sort of extinction. So anyway, so initially we sort of made this change of just the growth rate instead of constant. And then, of course, instead of a function of androgen, now will be function of cell quota, because the cell, what's the nutrient of outside doesn't matter. It's really what's nutrient inside cell that going to change the growth, change the switching rate, and so on. And these ones also really follows from the standard, the chemical sort of equations many people use. So I am not going to, I mean, this is not our invention either. This is the ecologists, we use this all the time. And we know this makes a lot of sense. All these parameters also can be evaluated and has a very clear biological, ecological meaning. So what I want you to see is, I have to speed up. So we were excited at first. We can really have the cycles. We use the F-mean search to choose the parameter value, but then we find that we cannot produce the law, the amplitude. And then when we did the parameter, the LO comparison, we find out actually our model is worse off in terms of point-to-point, I mean the solution and the point difference using the mean square LO comparison. It's actually less relevant. You're right. Yeah, right. But then still we want to, if you want to defend your model, you want to use some measurement, not just visual. So we scratched our head and we did several iterations in between. But finally we realized that we were not careful when we reading literature, including Tracy's paper, that when the Japanese group apparently misled by the notion that the androgen independent, so they assumed all the functions, all the coefficients, all those rates for the androgen independent one indeed doesn't depend on androgen, but that was a mistake. It's just that require lower one, like the Q2 will be a little bit lower. So we sort of like put back the androgen dependence for these rates. And so as an actual function of the cell quota, then we also fine-tuned of the PSA function instead of just a function relationship. Now we have a differential equation. Again, we have multiple reference to support this formulation. And now that's what you see the fitting. So with all the biology, sort of like the mechanisms incorporated into the model, then we not just have the cycles, but also the amplitude fit beautifully. And then we have also tried for all the data we have, the other 7 data, other 6 cases, they all fit very nicely, much better than what the previous 2 models. The either model, if you look at the total LO patient by patient, so you can see a very remarkable improvement. It's really one magnitude improvement. Of course, visually you can see that too. So this is really, usually I stop here, and probably that's also where I should stop today. I was hoping to talk about the second paper, which accepted months ago, and then it's now. I mean, you can download that online, but you can see I just downloaded this about a few hours ago. But I don't have time. I don't have time to go over this. This is to argue that we can even predict 8 months ahead of time, but then our model doesn't do much better than much simpler model than the piecewise linear equation, for instance. So that's really also scratching our, we are scratching our head why, or complicated model, or model that fit data so well, yet going, when looking at the prediction longer term, we cannot do much. But that probably makes sense because even for weather prediction, you really have to update your model a month, the weather prediction every 6 hours. So I think, so the answer to the question is yes, you can if you are looking at whether or not the treatment can be continued. If you want to look at the long-term precise prediction, no model can do that because there's a lot of other things that can happen in between. Yeah.
Yeah, but you are predicting somehow, you are predicting the future of certain established treatment because seeking data, you are basically seeking certain already established treatment. But now it seems like you have a beautifully confirmed model because this data pretty much. So maybe now you could use this model and try to analyze other scenarios of protocols and see what about if you give shorter periods, longer periods, maybe less dose for longer.
That's our summer. This is our summer program. We have 3 MBI undergraduate students and also 3 of my PhD students. They're going to work hard on many of these scenarios. Yeah, right. Exactly. Right. And it will be actually still time consuming because they really need to fit the data. Now we have 109 patient data that we need to come through. Thank you. I think I have to stop here.